All right, and we're back. How we doing, everybody? We doing good? Go home. It's Friday. Ready to go home? Had one day on. I was like, oh man, too much. All right. So let's finish up section 4.1, shall we? Okay. So we were talking about minimum and maximum values yesterday. Really, there are two kinds of minimums and maximums. There are local minimums and maximums, and there are absolute minimums and maximums. Remember, the definition of an absolute is that it's the y values that are greater or less than any other y values out of the entire function along its domain. And sometimes that domain can be closed, and sometimes that domain can be open, or all real numbers. It doesn't really matter. We just need to say that value, that y value at that point C, is greater than or less than any other point in the entire function. And then we talked about, well, what if it's just around that piece? Well, that's when we talk about it as a local maximum or local minimum. And that's where it starts to get ambiguous there with the word near, where it's near that certain value. Okay. We talked about endpoints. Don't forget, in a closed interval, endpoints can be absolutes, but they cannot be locals because of the word near, implying that it's got to be defined on the other side of that endpoint, and it's not. So therefore, that's why endpoints can't be locals, but they could be absolutes. I got a good question about the extreme value theorem and talking about local and absolute minimums and maximums. The weirdest case of the extreme value theorem is when we have something that looks like this. If you have A here and B here, and it's just a flat line. Because really, is there an absolute maximum? Is there a highest point? Yeah, I mean, there is a highest point, but it's also the lowest point, right? This is a case where the absolute maximums and minimums are the same. It doesn't go any higher or lower than those points. And you might be saying, well, wait a second, it's not higher than. Well, think about our definition of a local maximum or minimum, and we saw that there was an or equal to, right? And that means that it could be equal to. There could be points that could be equal to around there, but nothing higher than or nothing lower than those points. So if you've got a flat line like that, that's actually the case where the absolute maximums and minimum values are the same. It's at that point, that y value, that wherever the horizontal line is at. But that's the weirdest case of that. And then we ended with this thing called Fermat's theorem, right? Fermat's theorem. Pretty famous mathematician, Pierre Fermat. It's saying that if f has a local maximum or minimum value, if it has a local maximum or minimum value, then either, and it exists, and f prime exists, then f prime of C is equal to 0. Okay? Now, we ended yesterday saying that, but the converse is not necessarily true. The reverse of this theorem is not, it's usually true, but it's not always true. If the derivative equals 0, usually there's a local maximum or minimum value there, but not always. Like, think about the cubic function. I know we talked about this yesterday, but just going through it one more time. What's the derivative of x to the third? 3x squared. So you're saying that if I set that equal to 0, there could be a local maximum or minimum? Well, what's happening at 0 on x to the third? Is there a local maximum or minimum value there? No. And this is the counterexample, right? Because it's actually like flatlining in there. It's bending through that point. So that's where weird things can occur. If it bends through, you might get what we'll call here in a second a critical point that's not actually a maximum or minimum value. Okay, so you got to be a little bit careful. You got to be just a little bit careful. And there are times when, like this, is this differentiable on that corner point? No. Is there still a local minimum value there? Yes. So you have to be a little bit careful. You have to kind of understand what the functions are doing and what the functions are at any given moment, so to figure out what's happening with the derivative. Okay. They say, warning, examples 5 and 6 show that we must be careful when using Fermat's theorem. Example 5 demonstrates that even when f prime of c is equal to 0, there need not be a maximum or minimum value at c. Furthermore, there may be an extreme value that doesn't exist as the absolute value. Okay, now, this is important here. Okay, the book is going to call these critical values. I feel like, or critical numbers. I feel like in math, we've defined critical numbers to be like a bunch of different things. But the book calls critical numbers places where there could be a maximum or minimum value. Places that have the potential to be maximums or minimum values. A critical number of a function is a number such that f prime of c is equal to 0. It's where the derivative is equal to 0. Okay? Or where the derivative does not exist. Because those were the two then statements of Fermat's theorem, right? We had the derivative not existing, and we had the derivative is equal to 0. Those were the two pieces of the two weird parts about Fermat's theorem. Either the derivative does not exist, or the derivative does not equal 0, or the derivative equals 0. Okay? And those two places we are going to call critical numbers. Critical numbers. So if you see this in the book, it's going to say to you, find the critical numbers of this function. That's what it's asking you to do. Find where the derivative equals 0 and where the derivative does not exist. Now, when thinking about functions where points don't exist, okay, that's not always going to happen. Like if you end up with a polynomial as your derivative, polynomials exist everywhere, right? So that part about it gets thrown out. I could still figure out where the derivative does not exist, or where the derivative equals 0. Just find the zeros of that polynomial. But then if I talk about the derivative, if it ends up as a rational function, right? If the derivative ends up as a rational function, okay, then we have the potential that the derivative does not exist. So we have to take that into account, okay, to figure out where it does not exist. So let's take a look here. Find the critical numbers. Find the critical numbers. And there's a lot of homework problems that look like this, where it just says find the critical numbers. And again, the critical numbers are going to have two parts. They're going to have the where the derivative does not equal 0. Where the derivative equals 0 or where the derivative does not exist. Words keep getting mixed up. Okay. Now, the first thing I need to do is just find what the derivative actually is, right? You need to figure out what the derivative actually is. It's been a minute since we've done a derivative, hasn't it? Right? So I've got, looking at this function, it looks like I've got a little product in there, right? Got a product rule. So f g prime plus g f prime, right? Okay, now, f g prime plus g f prime. The two pieces are x to the 3/5 and then 4 minus x. So we got a polynomial-ish thing with a fractional exponent and then just a 4 minus x sitting on the inside. Okay, f is x to the 3/5, so that means I've got x to the 3/5 times, what is the derivative of 4 minus x? What's the derivative of 4 minus x? The 4 is going to go away. -1, right? So it's -1. Get to my right page, so I got everything good here. Perfect. So we got -1 here. Plus, okay, we got g, which is my 4 minus x, times the derivative of x to the 3/5. Okay, the derivative of x to the 3/5. Drop it down. We got 3/5 times x to the, okay, 3/5 minus 1 is what? Negative 2/5. So here's my derivative, right? Here's my derivative. Now, you have to simplify down because if you just set this equal to 0 and try to solve, you may be missing where the derivative may not exist. And here's what I mean. Okay, so this is a negative x to the 3/5 plus, okay, this is going to move down to the denominator with a 5 and a 3 staying up top. You follow me there? Okay. I'm going to distribute that 3 in, and I'm going to reorder it because I don't like a negative sitting out front. I'll just turn it into a minus. So this is a 12 minus 3x over 5x to the 2/5. 5 times x to the 2/5 minus x to the 3/5. Just like put that minus sign in between there. Yeah. Now, I have to get common denominators to put this all together, right? I have to get common denominators to put this all together. So what I'm going to do here is I'm going to multiply by, do this, multiply by 5x to the 2/5, this other denominator. Which will get me 12 minus 3x over 5x to the 2/5 minus, okay, now look here. I'm going to have a 5 times x to the what? If I'm multiplying with bases, don't I add exponents? So what is 3/5 plus 2/5? Right, 1, right? 5/5. So really that's just 5x over 5x to the 2/5. You follow me there? That was 3/5 x to the 3/5 times x to the 2/5. Just add exponents. So 3/5 plus 2/5 is 5/5. So really just 5x. Now we can subtract. So this is going to give me a 12 minus 8x over 5x to the 2/5. So there is my derivative. That's f prime, right? There's the derivative. Now, if we had not simplified that, we might not have seen that. What type of function is that? It's rational. Does this have the ability to not exist? Yeah. So you have to be careful. Look at the derivative. Analyze what type of function the derivative is, because now I can say that the critical points are, well, where this function does not exist, and it does not exist when the denominator equals 0. These are going to be my, I always abbreviate CPs, my critical points. So where the derivative does not exist, and also where the derivative is equivalent to 0. Now, in a rational function, how do you find the zeros of the rational function? Well, you just put the top equal to 0, right? Wherever the numerator equals 0 is the zeros of the rational function. Remember, when you're working with a rational, the zeros of the numerator are the zeros of the entire function. The zeros of the denominator are where the function does not exist. Okay, so just solving this one here, that's just x equals 0. Right? Divide by 5 and then take the 2/5 root of it. That's just 0. And then on the other side, that would be 12 is equal to 8x, and we divide 12 by 8, and we get 1.5. So these are my critical points. Now, what is that telling me? That's telling me that these are the potential places where I could have maximums and minimum values of the original function. Does that mean it will definitely have maximums and minimums at 0 and 1.5? No. It just means that these are the potential places where I could have maximums and minimum values. We're going to study how we figure out what they are and if they exist at those places. Right? We're going to look at that eventually within sections 4.2 and 4.3, how we tell what those places actually are. These are just my critical points right now. Okay, let's do that again. Oh yeah, we got to talk about the closed interval method. Okay, the closed interval method. Now that was for locals, right? That was for locals. Those were the potentials for local maximums and minimum values. Okay. If f has a local maximum or minimum value, then it is a critical number. This is kind of like this is Fermat's theorem kind of like restated, right? Using the book's terminology of being a critical number. It's just saying that if we have a local maximum or minimum value, then it occurs at a critical point, a critical number. Okay? Now, if we are talking about absolutes, to talk about absolutes, we first look at a closed interval. I'm just looking to see if that's the end yet. We first look at the in cases when we have a closed interval. This is called the closed interval method. Okay. There are going to be questions on the assessments that says, okay, use the closed interval method to determine the absolute maximums and minimums. So you just got to know what this process is. And now think about what the method is, a closed interval. So that means that this does not go on forever left and right. This is if we have endpoints, if it is in a closed interval. To find the absolute maximum or minimum values of a continuous function on a closed interval. Now, it brought up something that's not even not in the name of this, but it also has to be continuous as well. There can't be any discontinuities to use this method. So if you've got a jump or an infinite discontinuity, you can't use it. This has to be continuous and closed. To find the absolute maximum and minimum values on a continuous closed function on the interval a to b, whatever that interval is, from 1 to 5, from 0 to pi, whatever it is. And notice the brackets got to be closed. Okay. First thing you want to do is find the values of the function at the critical numbers of f. We just ran through the process of finding critical numbers. Those critical numbers are where the function does not exist or where the derivative is equal to 0. So you find the critical points and then find the value of the function. Run those critical points through the original function to see how high or low that goes, right? I know there are critical points at certain values, but there are critical points at certain locations, but I don't know where those locations are on the original graph. So what you do is you figure out how high or low that function goes at those critical points. Then you find the values of the functions at the endpoints. Because remember, the endpoints still have a possibility of being the absolute maximums or minimums. So to be an absolute maximum or minimum, you either have to be a local or an endpoint. So what we're doing here is finding the values at the locals, then finding the values at the endpoints, and then we're just going to see what's the biggest or smallest one. The largest values from step 1 and 2 is the absolute maximum. The smallest values from step 1 and 2 are the absolute minimums. Because those are the only possibilities of places. The endpoints or the locals. Step 1 is finding the locals. Step 2 is finding the endpoints. And then you just look and see what's the highest and what's the lowest. Okay? Can we try that? Can we do it? Let's do it. There's something already. I'll pause for a minute. Oh, while we're paused here, I did update the new syllabus for CCP people. You have a new syllabus for the second semester, and I did upload that to Schoology. So I would download that. Make sure you have it somewhere in your files. Okay. Find the absolute maximum and minimum values of the function. First off, can I use the closed interval method? Well, is this a closed interval? Yeah, look, or equal to -1/2 and up to 4. Closed interval. Is this continuous on that interval? Well, what type of function is this? It's cubic. Cubics are all continuous, right? We talked about continuity a lot in the first semester. So we should be able to tell if certain functions are going to have the possibilities of discontinuities. This does not have any possibility of any discontinuities. It's a cubic function. It's polynomial. Okay. All right, so I know that this is continuous and closed. So I can use the closed interval method. And the closed interval method says, well, find the critical points. And the critical points are where the derivative does not exist or where the derivative is equivalent to 0. So let's find the derivative. Oh, pretty simple derivative here. 3x squared minus 6x. There's f prime. The 1 goes away. We got 3x squared minus 6x. Okay, so there's my derivative. This is, let me move that over a little bit. This is f prime. Okay, does f prime ever not exist? What type of function is the derivative? It's a quadratic. Does the quadratic function ever not exist? No, it's always going to be existing, right? There are no x values that are undefined here. Remember, the possibility, like rational functions are when we get things that are undefined. Square root functions are when we get things that are undefined. Weird functions like that, like logarithmic ones, we get functions sometimes when it's undefined. But for a polynomial, it's defined everywhere. The domain is all real numbers. So the only critical points I'm going to have are where the derivative is equal to 0. Factor out the x. Actually, factor out a 3x. I'm going to get an x minus 2. So we get x equals 0 and x equals 2. So those are my two places. Those are my two critical values. Okay, so step 1, find the critical points. Step 2 would be run the endpoints through the function. I like to make myself a little table. Like the farthest left this function is going to go is -1/2. Then I'm going to hit 0. Then I'm going to hit the critical point 2. Then I'm going to get to my endpoint 4. Right? Those are the x values where I have the possibility of having an absolute maximum or minimum value. These are the endpoints and the locals. Endpoints, locals. Okay, now, all I'm going to do is run them back through the original, not the derivative. Don't run these through the derivative. Okay? I don't want to do that because, look, if I put 0 back into the derivative, it's going to give me 0. If I put 2 back into the derivative, it's going to get me 0. So I got these numbers, right? Put them back into the original. That's going to tell you the y value at that point. So I have -0.5 to the third minus 3 times -0.5 squared. Right, -0.5 to the third minus 3 times -0.5 squared plus 1. And that's going to give me 0.125. Plug 0 in. Well, 0 minus 0 plus 1 is 1. Plug 2 in. Okay, so that's, I better do it in my calculator. 2 to the third I know is 8. Minus 3 times 2 squared is 4. Plus, oops, that's a minus. Plus 1. -3. And now we plug in 4, the other endpoint. 4 to the third minus 3 times 4 squared plus 1. 17. Okay. So what is my absolute minimum value? What is my absolute minimum value? Which one's the smallest value here? -3, right? So there is an absolute minimum. My absolute minimum is -3. And where does it occur? At x equals 2. My absolute maximum is 17, and it occurs, oh, that's an x. X equals 4. Yeah, there we go. Make sense? That's the closed interval method. You find the critical points, you run them through with your endpoints back into the original function, and you see which one's the highest and which one's the lowest. Okay. Let's do that one more time. Use a graphing device. Actually, we're gonna do part B and then we'll do part A. Do part B first. I don't want to be swayed by any calculator. Use calculus to find the exact minimum and maximum values. And it looks like I have a function f of x is equal to x minus 2 sine x on the interval 0 to 2 pi. Now, can I use the closed interval method? Is it a closed interval? Is it continuous? Yeah, because how can we verify continuity? Well, remember, continuity of the pieces is the continuity of the whole, right? So x, that's continuous everywhere. That's just a linear function, right? And sine x, okay, yeah, that's continuous as well. It's just going to keep going on forever. It's never going to have any discontinuities in it. So it's continuous and it's closed. So that must mean that I need to find the derivative. This is for my critical points. I need to find the derivative. Right? Okay, what's the derivative of x minus 2 sine x? What's the derivative? 1 minus 2 cosine x. 1 minus 2 cosine x. Derivative sine is cosine. So there's my derivative. Now, for my critical points, I need to figure out where the derivative does not exist or where the derivative is equal to 0. Does this ever not exist? Are there ever any discontinuities in this? No. It's cosine, right? It's going to wave. So it's never going to have any discontinuity. It's never going to not exist anywhere. So therefore, I just need to see when this is equal to 0. And that's going to tell me where my critical points are. So let's just solve that little equation. We say we add the 2 cosine x over to the other side. So 1 is equal to 2 cosine x. Divide by 2, 1/2 is equal to cosine x. Okay, big question of the day. What angle gives me a cosine of 1/2? Ooh, pi over 3, good. Pi over 3. What's the other one? Yeah, 5 pi over 3, 5/3. Or 5 pi over 3. Why don't I keep talking about plus 2 pi n? Well, because this was a closed interval. I only wanted it from 0 to 2 pi. Right? We would be correct in saying that we would have to think about all rotations, but because this is closed interval, I can just use those two. So I got pi over 3 and 5 pi over 3. Those are my only critical points. So closed interval method says, let's do the endpoint, the smaller endpoint, and then that brings me to pi over 3. And then that brings me to 5 pi over 3. And then that brings me to 2 pi. Okay, now let's run each one of those back into the original. Okay, let's run each one of those back into the original. Not my derivative, but my original. So for example, 0. That's going to give me 0 minus 2 sine 0. Am I in radian mode? I am in radian mode. Okay, good. 0. So I know the output here is 0. Same thing with 2 pi, right? Isn't going to give you the same output value? Let's test that, though. Let's just be sure. 2 pi minus 2 sine. 2 pi. I could be wrong. Wait a sec. That might not give me 0. Now that I'm thinking about it again. Yeah, that's 2 pi. It's going to give me the exact same thing. It's 6.28. 2 pi is going to give me 2 pi. You know why? Because that's going to be 0 again. That's what it was. That's going to be 0 again. So it's 2 pi minus 0, or just 2 pi. What was it? 6.28, yeah. Okay, now let's find pi over 3. Pi over 3. So this is pi over 3 minus, okay, we got 2 sine pi over 3. 2 sine pi over 3. Negative 0.68. So far, that's winning for absolute minimum, right? Okay. Let's check 5 pi over 3. So we've got 5 pi divided by 3, 5 pi over 3, minus 2 sine, I'll do this again, 5 pi over 3. I don't know if that parenthesis is necessary, but I don't think so. 6.97. I could find exact values of those, like plugging in pi over 3 and figuring out, okay, the y value of pi over 3 is, the radical 3, we would do that, but radical 3 over 2, but we don't need to do that. Because honestly, doing it as an exact form is going to confuse us because we need to see it in relation to the others. So because I put it as a decimal here, I can see that 5 pi over 3 is going to get me a bigger value than 2 pi, right? The y value of 5 pi over 3 is going to be bigger than the y value at 2 pi. So therefore, this is my absolute max, and this is my absolute minimum, right? So let's formally state it. I shouldn't just arrow it. The absolute minimum is equal to negative 0.68 at x equals pi over 3. And then the absolute maximum is 6.97, and that occurs at 5 pi over 3. Okay, so we did it with calculus. Let's do it with our graphing calculator, just to kind of verify, right? To show you this is what we're actually doing. Okay, so the original function, get this out of here, turn off the plot, was x minus sine x, or sorry, minus 2 sine x, excuse me. X minus 2 sine x. Now I'm going to manipulate my window a little bit because I know I only want the interval from 0 to 2 pi. So let's get these x values out of here. Oh, did I make you freeze? Oh, I can't. I have to choose something. So let's go a little bit below 0, like negative 0.1 or negative 0.5. We'll go like half a unit. Why didn't you go negative, sir? Negative 0.5. And then x maximum, okay, I want to go to 2 pi, but let's go just a little bit above 2 pi. So 2 pi is 6.28. So let's say 6.5. And then the y minimum looks like my smallest value is negative 0.68. So let's go a little bit below that. Let's go negative 1. And then my highest y value is 6.97. So let's go let's go a little bit high, 7.2, 7.3, something like that. And I am going to graph. Okay. So do we see, based on just what I see on my screen, the highest and lowest points? Yeah. Do I see it here and here? Let's actually find where those values are using my calculator. Remember that your calculator can calculate minimums and maximum values. Because you're going to calculate locals. So let's do minimum. And now my minimum is down here, right underneath the letter O and bound, right? So what I have to tell my calculator is, okay, I'm going to go down here. Sorry, this kind of gets a little weird because you can see my cursor down there. It's right there. I want to go somewhere to the left of the dip and then somewhere to the right of it, because all your calculator is going to do is run some numbers really quickly to figure out what the lowest possible that it got. What was the lowest possible? Negative 0.68. What we see. Where did it occur? at 1 point, I can't even see that decimal, 1.0 something. I'm guessing that's pi over 3. Yeah, 3.14 over 3, 1.0 something. Let's find the highest point. Second, calculate the maximum value, the 4. It's going to ask me left bound, right bound guess again, but now I want to go up and over here. So I'm going to arrow over until I'm somewhere to the left of my bump, and then I go somewhere to the right of my bump, and then I guess somewhere in the middle there, and there it is, 6.97, rounded, 6.97, right? And at 5.24, I'm guessing that's 5 pi over 3. 5 pi divided by 3. 5.23, exactly where we thought it was going to be, 5.24. Okay. So you can use your calculator to find those certain points as well, but you're going to need to be able to do it without your calculator as well. Okay. Questions about that? Okay. That is section 4.1. All done. Turn off the video.